Two freight cars roll down the same track. One leaks sand through a hole in its floor, losing mass every second. The other catches grain blown in from a neighboring car, gaining mass every second. Newton's second law still runs the show, but for one car, the changing mass leaves the equation of motion untouched, and for the other, it adds a whole new term. The difference comes down to a single question. Does the transferred mass carry momentum? We sorted mass flow problems into 4 categories by that same question, and today we work the 2 freight car classics, sand leaking out of a moving car and grain blown into one. First, the tool. It is tempting to write momentum as mass times velocity and differentiate by the product rule, m times dv dt plus v times dm dt. Resist that. Momentum was defined for a system of constant mass, and the shortcut is only valid when the transferred material carries 0 velocity in your reference frame. Worse, the leftover term v times dm dt changes value from one reference frame to another, a sure sign it is not a general law. Here is the safe procedure. Choose a fixed collection of matter. Write its momentum at time t. Follow the same matter, including any piece that leaves or arrives, and write its momentum at t plus delta t. Subtract, divide by delta t, and take the limit. The total external force equals that limit. Both examples run on exactly this procedure. Our first example, emptying a freight car. A car of mass sub c holds sand of mass sub s. At time 0, a constant horizontal force of magnitude F begins pushing the car forward, and at the same instant, a port opens in the floor, so sand streams straight down and out at the constant rate b. The car starts from rest. Find the speed of the car when the last of the sand is gone. Point the positive x direction along the motion. Take as a system the car plus whatever sand is still inside at time t, combined mass m sub c of t, moving with velocity v sub c of t. So the system's momentum at time t is m sub c of t times v sub c of t. Now follow that same matter through the next interval, delta t. A small element of sand, delta m sub s, drops out, so the car's mass changes by delta m sub c, which equals minus delta m sub s. The car ends the interval moving at v sub c plus delta v sub c. And here's the key physical fact. The sand leaves straight down through the floor, so horizontally it separates from the car while moving with the car. The momentum diagram at t plus delta t therefore shows 2 pieces, the lighter car and the departed sand element, both moving at v sub c plus delta v sub c. Drawing all the departed sand at the final velocity is an approximation. Sand leaves continuously, so its velocity really ranges from v sub c up to v sub c plus delta v sub c, but the car's mass changes continuously in exactly the same way, and in the limit, those 2 contributions to the system's momentum cancel exactly. Add the momenta at t plus delta t, delta m sub s plus m sub c plus delta m sub c, all times the common velocity. Since delta m sub c equals minus delta m sub s, the mass changes cancel, leaving m sub c of t times v sub c plus delta v sub c. Subtract the momentum at time t, and the change in the system's momentum is just m sub c of t times delta v sub c. The departing sand has vanished from the bookkeeping. The only external horizontal force is F, so F equals the limit of that change over delta t, which is m sub c of t, times dv sub c dt. Newton's second law in its familiar shape, with the mass now a function of time. Notice what is not there. No dm dt term. Mass leaving with 0 relative velocity leaves the equation of motion untouched. Switch the force off, and a rolling leaking car would hold its speed exactly. Now the mass function, sand drains at the constant rate b, so the sand gone by time t is the integral of b, which is b times t, and the car's mass is m sub c plus m sub c minus bt. The equation of motion reads F equals m sub c plus m sub minus bt times dv sub c dt. Separate variables, dv sub c equals f dt over m sub c plus m sub s minus bt. Integrate the left side from 0 to v sub c of t and the right side from 0 to t. The right side is a logarithmic integral minus f over b times the natural log of m sub c plus m sub s minus bt prime, evaluated between the limits. A difference of logs is the log of the ratio, and the flipping the ratio flips the sign, so the speed comes out as v sub c of t equals f over b times the natural log of m sub c plus m sub s over m sub c plus m sub s minus bt. Check the sign. The numerator is at least as large as the denominator, so the ratio is at least 1. The log is non-negative, and the speed grows as a pushed car must. The sand runs out when bt equals m sub s at time m sub s over b. Substitute, and the denominator collapses to m sub c alone, the empty car. The final speed is f over b times the natural log of m sub c plus m sub s over m sub c. Hold on to why that stays simple. In every mass flow problem, the potential extra term has the same shape. The mass rate, dm dt, times the relative velocity, the velocity of the transferred material minus the velocity of the car. Sand dropping through the floor moves with the car horizontally, so the relative velocity is 0 and the term dies. The car loses mass and its motion never feels the loss. Grain blown in from a neighboring car is different. It arrives carrying that car's horizontal velocity, u, in general not equal to the receiving car's velocity, so the relative velocity is not 0, the extra term switches on, and it acts on the car like a force. That is the second example. The second example, filling a freight car. Grain is blown from car B into car A at a constant rate B in kilograms per second. The grain leaves the chute falling vertically, which means it still carries car B's horizontal velocity, u. Car A starts from rest with mass m sub a0. Find car A's speed as a function of time. That phrase, falls vertically, is where intuition slips. Vertically is relative to the chute on car B. Seen from the ground, every bit of grain arrives moving horizontally at u, loaded with momentum, and car A must absorb it. Point positive x in the direction of motion and choose the system with care. Car A plus the grain already aboard, combined mass m sub a of t, plus the small element of grain, delta m sub g, that will be blown in during the next interval. The same matter at both instants. At time t, car A moves at v sub a of t, while the incoming element still moves at u, so the system's momentum is m sub a of t times v sub a of t, plus delta m sub g times u. By t plus delta t, the element is aboard, a single mass, m sub a plus delta m sub a, moving at v sub a plus delta v sub a, where delta m sub a equals delta m sub g. No external force acts along the track. The transfer is internal to this system, so the limit of the momentum change over delta t is 0. Expand the product and subtract the earlier momentum. 3 pieces survive, m sub a times delta v sub a, delta m sub a times v sub a minus u, and delta m sub a times delta v sub a. Divide each by delta t and take the limit. The last piece is the product of 2 vanishing quantities, a second-order differential, so it drops out. What remains is the differential equation. 0 equals m sub a of t times dv sub a dt, plus dm sub a dt times v sub a minus u. There it is, the extra term the sand problem never had. Mass rate times relative velocity written here as v sub a minus u. Rearrange, writing b for the constant rate dm sub a dt, dv sub a dt equals b times u minus v sub a over m sub a of t. We cannot integrate this over time directly. The mass in the denominator is itself a function of time. So separate variables against mass instead. dv sub a over u minus v sub a equals dm sub a over m sub a. Integrate the left from 0 to v sub a of t, and the right from m sub a 0 to m sub a of t. Both sides integrate to logarithms. The natural log of u over u minus v sub a equals the natural log of m sub a over m sub a 0. Exponentiate both sides and solve for the velocity. V sub a equals m sub a minus m sub a 0 over m sub a times u. Read that result. The car's speed is u times the fraction of its current mass, that is grain. And since grain arrives at the constant rate b, the mass at time t is m sub a0 plus bt. Substitute v sub a of t equals bt over m sub a0 plus bt times u. The speed starts at 0 and climbs toward u. Car A approaches car B's speed, but never passes it. The same answer comes by a second route, and the agreement is a useful check. This time, substitute the mass function first. dv sub a dt equals b times u minus v sub a over m sub a0 plus bt. Separate variables dv sub a over u minus v sub a equals b dt over m sub a0 plus bt. And keep that factor of b, it belongs in the time integral. Integrate the left from 0 to v sub a of t and the right from 0 to t. The left gives the same log as before, the natural log of u over u minus v sub a. On the right, the antiderivative brings out a factor of 1 over b, which cancels the b in the numerator, leaving the natural log of m sub a0 plus bt over m sub a0. Exponentiate both sides. U over u minus v sub a equals m sub a0 plus bt over m sub a0. Solve, and the algebra lands on the same result. V sub a of t equals bt over m sub a0 plus bt times u. Two different integrations, one answer. Now the prettiest check of all. Multiply both sides by the car's current mass, m sub a0 plus bt times v sub a of t equals bt times u. Read each side. The left is the total momentum of car A with its cargo at time t. The right is the mass of all the grain delivered so far, the bt kilograms, times the velocity u each bit arrived with. The system's momentum equals exactly the momentum the grain brought in. With no external force along the track, momentum is never created, only handed over. The whole differential equation was conservation of momentum, keeping the books one instant at a time. Set the two cars side by side. The emptying car loses mass straight down at 0 relative horizontal velocity. The extra term, mass rate times relative velocity, vanishes, so the equation of motion is simply F equals m of t times dv dt. The shrinking mass only makes the car respond faster to the same push, and the speed grows as a logarithm. Remove the force and the speed holds constant, leak or no leak. The filling car gains mass at relative velocity u minus v sub a. The extra term is alive, it acts like a thrust, and with no applied force at all, it drives the car from rest toward u. One momentum principle, one procedure, fixed matter, two snapshots, subtract, divide, take the limit. And a single term deciding both outcomes. That term, mass rate times relative velocity, powers everything ahead. The fire hose driving a boat forward, and the rocket, which throws mass backward fast on purpose. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.